Hello! Let's have fun with equilibrium. So with equilibrium, we talk a lot about what an equilibrium constant. And so what does that even mean? And so the whole idea is that not all reactions go all the way to completion. We don't make 100% products usually. It'd be nice, but that's just not the way the real world works. So we need some value that tells us about how far a reaction goes, and then what the ratio of products to reactants is going to be. So that's what the equilibrium constant tells us about. So KEQ tells us about the ratio of products to reactants. And so you can see below how we write KEQ given a reaction. And we want to take into account the concentrations of the different species as well as the coefficients in front of them. So the coefficients now become the exponents. And so sometimes I'll write this like products to their coefficient divided by reactants to their coefficients. Okay, and so we can go ahead and practice writing some of those expressions, but we have to keep in mind what gets included. And so we only include gaseous or aqueous species. So that means solids and liquids are not included. Okay, you can't really talk about the concentration of a solid or liquid. Instead, we talk about their activities, and we say that they're pure solids or liquids, and so their concentration is sort of like 1. So we'll just use a 1 there. And so for this first reaction, we have all gases, so we'll include everything. We'll have KEQ equal to the concentration of water squared divided by the concentration of H2 squared times O2 squared. They're not squared, I'm sorry. Okay, it's just products over reactants, their coefficients. And you do want to keep your eye out for water, because water can either show up sometimes as solid, liquid, or gas, but we only include it when it's in the gas form. Okay. For this next reaction, we have calcium chloride, which is a solid, and so we don't want to include that, or we'll call it just 1. So our KEQ is going to be equal to the concentration of calcium ions to the power of 1 times the concentration of chloride ions squared for that coefficient. And then we can write over 1 if you'd like to represent the solid calcium chloride. Okay, and then we have the silver chloride reaction. And again, we have a solid, so we're not going to include that. We'll just say KEQ is equal to 1 for that solid, then divided by the concentration of silver ions times the concentration of chloride ions. Okay, so it's not too bad to write those expressions, just make sure you slow down and pay attention to the phases and to the coefficients. So the size of KEQ can tell you about how much product or reactants are present at equilibrium. And so since we're thinking about products over reactants, if we have a big K, or so K greater than 1, that means we're going to have a bigger numerator, right, in our expression. And so we're going to have more products. and we'll have KEQ greater than 1. And then the opposite is true if we have a small KEQ, or where K is less than 1, because that means we have a big denominator. And so we have more reactants. So we say if KEQ is less than 1, we say it's reactants favored. And then if they're equal, or if KQ equals 1, would just be a special scenario where we happen to have half products and half reactants, and similar. So they're present in similar amounts. Okay, so we're going to talk about so many different equilibrium constants, but they all come from that basic products over reactants relationship. The only thing is, sometimes we put a different subscript to represent different scenarios. And so eventually throughout Chem 112, we'll talk about all of these Ks. There's no need to be stressed, because they're all just still specific cases of KEQ, which is going to be our products over reactants. And so we've talked a little bit about KP versus KC. And so KP just means that when we plug in numbers to our expression, that they happen to be in ATM. KC would be the same expression, except we would plug in molarity. Okay, so don't let the subscripts trip you up too much, because they're all coming from the same relationship. Okay. Enough talking, let's do some problems. Here we have the much discussed Haber process, and they give us equilibrium concentrations below, and they want us to figure out what KEQ is. It's never a bad idea to start by writing your KEQ expression. So let's go ahead and do that. We'll have NH3 squared divided by N2 divided by H2 cubed. Okay, so we have that. And to figure out what that value is, we can plug in equilibrium concentrations, and that's what we happen to have here. So these are the concentrations that they measure when it seems like the reaction's not changing, or once the rate forward becomes equal to the reverse rate. So we can go ahead and plug in those numbers. So we'll have 7.2 ATM squared divided by 2.1 ATM divided by 3.5 ATM cubed. And then we just plug that into our calculators, being really careful with the division and the different exponents. And when we do that, we get a value of 0.58. And so this technically is going to be a KP just because we put atmospheres in, so P for pressure. Okay, so now we're at a different temperature, so we have a new K. So the only way to change your equilibrium constant is to change the temperature. So they give us some initial concentrations, and they want us to figure out what the concentration of the NO will be at equilibrium. So, when in doubt, we're going to ice it out. Okay, yeah, we're going to ice it out. So let's go ahead and do that on the next slide. So, when in doubt, ice it out. So let's remember what ice even means. Here we have I, which is going to stand for initial concentrations. C is the change. And E is equilibrium. So the problem tells us we're starting with 2 molar N2 and 2 molar O2. So we can go ahead and put that in here. We always want to put molarity into an ICE table. So make sure you have that. If they give you moles and volume, you get molarity with just moles per liter. And they don't tell us anything about the NO, so we can just say we don't have any of it to start. So if we don't have any of it to start, we got to make some. And so we'll add to it, and we'll have some change, but this will have a 2 times whatever that change is because we have the 2 in the coefficient. Whereas the N2, which we're going to use up, we're just going to use 1 times the change because we just have a coefficient of 1 there. And then the same will be true for the O2. We'll just have minus 1x. Okay, so we're losing some amount of x from the reactants, and we're making 2x on the right. Then for our equilibrium row, we're just going to combine the 2 rows we have. So we'll have 2 minus x for N2 and O2. And then we'll have 0 plus 2x, which is going to be 2x for our NO. But we have to remember that as responsible chemists, we're going to write our equilibrium expression. We'll have NO squared divided by N2 O2. So now what we're going to do is take the equilibrium row and put it into our equilibrium expression. And then we can do some algebra. So we'll have 4 is equal to 2x squared. And make sure you square the whole thing, not just the x. It's 2x all squared. Now divided by 2 minus x times 2 minus x. Okay. And this is where it's good to be on your toes, because then you can see I have 2 minus x times itself. So I'm going to just change this denominator to be, 2 minus x squared. And that's nice because it gives us a way out of doing the quadratic equation. And we just take the square root of both sides and end up with a simpler formula of 2 equal to 2x divided by 2 minus x. And then we just multiply over. We get 4 minus 2x is equal to 2x. So we get 4 is equal to 4x. So x is equal to 1. We want to slow down and remember what x is referring to. This is referring to some molarity for the change. And then we can bring that back into our table to get the final real equilibrium concentrations for our different species. So for N2, we'll just have 2 minus 1, so we'll have 1 molar N2. We'll have 1 molar O2. And then we'll have 2 times 1 molar NO. So we'll have 2 molar NO at equilibrium. Okay, so if you're ever unsure about what to do, just go ahead and set up an ICE table write your K expression, and sometimes that can just help you see the different pieces and then eventually how to pull it all together. So we have KEQ, and we know that it's the ratio of products to reactants at equilibrium. We have this other expression, Q, and we can see that it's very similar the way it's written to KEQ. So all the reaction quotient is telling us about is where we are kind of in relation to equilibrium. So it's the ratio of products to reactants at any given time. And so usually we refer to this as like what it would be at our initial scenario. Okay. And so at any time we could be at Q, but the goal is to always get to equilibrium. Or to get to that ratio of KEQ. Okay, and so the way we do that is we plug different concentrations into Q, and we see how it compares to K. So when Q is less than KEQ, that means our denominator must be too big to make because the number ends up being smaller. So that means we have too many reactants. So that means we need to use some of those up, make more products. So the reaction is going to proceed to the right. It's going to go to products. And then the opposite is true then if Q is greater than KEQ. That tells me we must have too big of a numerator. So that means we have too many products. And so the reaction is going to proceed in the reverse direction toward reactants so that it can use up some of those products, make more reactants, and get to the desired place, which is when KEQ is equal to Q. So when they're the same, that means we're at equilibrium, and the reaction's not going to shift anymore. It's just going to continue to hang out there in its happy valley of equilibrium. So we sometimes say, well, hey, we're at equilibrium, and we add something to our reaction. What happens then? So, and that's what we use the Le Chatelier's principle for. So basically, if we add something to one side, the reaction shifts in the other direction. So, in this first scenario, we have this Haber process again. If we add in N2, we're adding more reactants. So you can also think of it as if we add more reactants, our Q is going to be smaller. Q will be less than K, and so the reaction is going to shift to the right. Or you can just think if I add something to the reactant side, it will shift to make more products. Okay. And then now for the next one, we're removing some of the ammonia. So we're removing a product. We're removing a product. Again, our Q is going to get smaller, and our Q is going to be less than K. So we'll proceed in the forward direction. Another way to think about it is if we're removing some of this product, we're kind of making a hole of sorts, and so the reaction is going to proceed this way to make up for that loss. And so we have a similar thing here for the H2. If we remove some of the H2, the reaction's going to shift to the left to make up for that loss. And in this scenario, if we are removing some of our reactant, our Q is going to be greater than KEQ, so we'll shift in the other direction. Okay. When you talk about heat, then we have to look at the problem and look for what it's telling us about delta H, whether it's endothermic or exothermic. And so here, if we can read and see that the reaction is exothermic, heat is exiting, we have a negative delta H. And so we can write heat in here as a product. So if we increase the temperature, heat the container up, we're essentially adding in more of a product. And so the reaction will shift in the other direction. And then if we cool it down, the opposite's happening. We're removing some of a product, so we'll shift to the right to make more. And then for volume considerations, if we have sort of like buying a house or living in the dorm rooms. So if you have a house with only one bedroom, you might want to live there by yourself. But if you move into a mansion, now you have the space for roommates. And so these people that you'd be living with are sort of like moles of gas. And so if you have a small volume, you don't want to have as many roommates or as many gas molecules. If you increase the volume of your container, you're willing to have more roommates or more gas molecules around. So if we decrease this, we're going to shift toward the side with fewer moles of gas, which is going to be the right. So on the left we have 4 moles of gas. On the right we only have 2 moles of gas. So we're going to shift right. And then oppositely, if we increase the volume, now we have room for those other moles of gas around. And so the reaction would shift to the left. Okay, so to make more ammonia, we'd want to run this in a cold container that also happens to be pretty small. Something to consider that's not written on here would be if we added something like xenon gas, so a gas that's not a part of the reaction, and we would say that this won't change the equilibrium at all. It won't change Q, so we're not going to have any shift associated. And this doesn't make so much sense for the Haber process, but if you change the amount of a solid or a liquid, it's not going to change the equilibrium either. You're not going to have any shift. So only things that go into your Q expression will have any shift effects. Okay, and so that's the end for equilibrium. I hope you guys have good luck. And don't forget that equilibrium is related to kinetics and how they're related. And to stay strong, you guys can do it. Bye.